Now what I really want to talk about is exactly this thing about using rounding to check the correctness of your answer. It's not as simple as the book tries to believe. Not by a long shot. And that, in fact, was the original motivation for writing this chapter. So the origin was actually, it's quoted in the book. It's from a textbook, which gave more or less like this, but a little extreme. That it's an older series. It was the book that I quoted from is in the late 90s was the best-selling middle school series in mathematics. It's the Addison Rescue. So what it gave was, so they wanted, that book wanted to illustrate the efficacy of rounding in helping you decide whether a number is right or whether the congregation is right or wrong. So that's the example used. So, okay, first of all, she said, never mind what the correct answer is. Let's have a rough idea. Let's say, so we round to the nearest hundred. Good, right? So that's what you now know this, right? And that would be, therefore, this is the rounded figure. $400, right? So the book says, without lifting a finger, you already know it should be roughly fine. Now you do it, and of course you do it, and then it's some 1, and it's 4 and 1. And the book says, 4 and 1 is so close to the rounded figure, you know that you're probably doing something right. Now, of course, that book commits the same error as what's in here, namely, yes, more or less you agree, 411 is quite close to 400, except who's to decide whether a difference of 11 is a small amount or big amount. Right? So the implicit assumption here is that if the difference is only 11, it's close. You believe this? What if your correct answer is 31? Your estimate is 20. That's the difference. This is the estimate. The actual answer is 31. What the difference is 11? Do you think this is close to this?
A lot.
What?
That's too much.
You're off by 50%, isn't it? At least. So what this masks, on one level, right away, is it masks a dishonesty about what's meant by close. 11, difference of 11 in this situation, when the correct answer is 31, your estimate is 20. Well, you're not going to say the difference of 11 here shows that this is close to this. Not at all, right? That is one problem. But a more serious problem is the following. Does anyone see what's wrong with this? A problem like this? Take one more. Give you 20 seconds. More or less.
One runs down, one runs up. Yeah. So you lucked out.
They have purposely chosen an example in their favor. Make you believe that rounding to near 100 under any circumstances is going to be a good method. Well, that's very serious mistake. Sorry? What's wrong?
Oh, yeah.
Oh, I see.
I
thought you were saying that doesn't work.
No, you're fine.
I'll give you an example. Okay, do the same thing, right? Never mind what the answer is. Let's see. Let's round it. So it's 200. That's 200. The answer should be 400. Correct? All right, add it. What do you get?
490.
Do you think 490 is close to 400?
No.
All right, now I'm going to press you more. Why do you think 400 cannot be said to be close to 490? You know quite well you have something in mind, but you're not saying it. But I want you to say it. Why do you think that's not close enough?
There's 100, that's 500.
Yeah.
Okay, that's a crude way of putting it. You're going to say it much better. Yes?
Like, you were just talking here about more than 50% off. Well, this is the same thing. It's on more than 20% off.
Exactly. You get the idea? This is the true answer, right? That's the true answer. The estimate misses the true answer by 90. But it's 90 out of 490,
Right.
which is like more or less 21 or 22 out of 500.
Yeah.
No, no, sorry. It's more like, okay, look. The difference is 90, right?
Yeah.
Compared with 490, you see
1/5 is what I would guess.
this one. More or less 20%. It shows someone have a calculator. Well, you buy
Yeah,
it.
okay.
This is bigger than 590. Oh, sorry, we have done having an fraction, so but you believe it, right?
18%.
And that's 18%. If you had 18% error, do you think that's close? That's very serious.
But it still depends also. It still depends.
Depends on what?
I think it still depends.
No, depends on
I'm just trying to give you an example of where 18% might be acceptable.
Oh, no, in context. You are saying this is good enough to judge accuracy. That's one. No. I can understand. You see, this is what's objectionable about textbooks. It seems like, just an arithmetic error. But it's not. It's a fundamental conceptual error. When you just say, well, choose numbers like this, and you can see, wow, this is great, you're misleading a whole generation of students into believing it. You want to add two three-digit numbers, it's perfectly okay. Check it by rounding to the nearest hundred. Think about that for a second. It's absolutely wrong. Because most of the time, you're going to have big errors, 10, 15%.
Yeah.
Now, there's no way anyone's going to tell you what kind of error is acceptable error. But by rule of thumb, they say anything less than 10% is more or less tolerable. I think no one is going to fight you for this. And anything bigger than 10%, you might want to think twice. As I said, there's no universal agreement. Who's to say? But I think you can trust yourself. More than a tenth is not so great. Therefore, suppose we pursue this. You really want students to have a good idea of rounding. In other words, how to use rounding effectively. You have to teach something different. Namely, you don't just say round, and that's it. And then you eyeball and say, is it close enough? Is it good enough? Is it reasonable enough? That's not what you do. What we do in mathematics is always precision. Precision, even in the face of imprecision, right? Making estimate is to be imprecise, one purpose. Therefore, you should be very precise about how imprecise you're going to get. This is the concept of relative error. What's called relative error is this is a fundamental concept. It's the absolute error divided by the true value. Absolute error, you know what that is, right? Means the real value compared with the estimate, you take the difference. Difference between two numbers means, of course, right? Big number minus small number. That's the common understanding of that word. Correct? Right? Or if we say the absolute value of the difference. This is important. You make every time you make an estimate, you always ask, what is the relative error? If you cannot answer that question, you better not say anything, because you're not entitled to saying anything. You're just bluffing. Right? So you have to be attuned to this fact. So in this case, that's exactly what we just tried to express. The relative error is just too big. Right? In this case, the true value is 490, is it? That's the true value, right? What's the absolute error? Well, the absolute error is 490 and 400. So this is 90 over 490. Can someone just check this? What this is? 18?
If you round.
I think probably a little bit more, right?
18.3.
Or 18. Okay, so 18. Fine. 18. It's okay.
Yeah, this close to 18.
That's enough. An 18% error is not going to be small. So now you want to be responsible. You want to tell students a useful way of checking your answer by rounding. And you don't tell them round to the nearest hundred. What do you think? So what would you suggest? Nearest 10, of course. I mean, try it at least, right? Round the nearest 10. Round the nearest 10. Now we're gonna. This is not something you're used to, right? So let's do it together slowly. Make sure you get it, right? I'm gonna estimate. No matter what the numbers are. So let's say 3-digit numbers. 2 3-digit numbers. You add 2 3-digit numbers, right? So that's something like. It's hard to write this, right? Okay. Yeah, I'll be right. I did it in the book. I don't know how I did
Do you
it.
want a 3-digit number or?
I just want to write those 3-digit numbers.
3-digit,
Right?
127 and 284.
Yeah.
Oh, that's a good one. So 149 and 127. No, we just did that.
Just do this again.
Okay, that's fine. Right. So I'm going to fudge it along the way so that we don't depend on this explicit number. So you round it off. Okay. So then you get 400. Now, what? No, that's too good.
Yeah, this is good. Yeah, this is a good one.
No, I don't want that.
That one is.
No. Let's say
149
let's say
and 147.
149
and 147.
Yeah, let's do that. So now we round to the nearest 10. Okay. Well, then 149 becomes what? 150. 147. 150. We get 300. True value. 6. Okay, what's the relative error? It's 300 minus 296 over 300. Oh, 296. Sorry. That's 4 over 296. That's roughly
1%.
yeah. And by any standard, 1% error is very good. Now, that doesn't entitle you to say, do it all the time, because there's only one pair of numbers, right? So the argument that you might want to learn is like this. Again, that's what I have trouble writing down, but let's talk about it and you see. Right? In that case, when you round like this, what could the absolute error be? Any two for any so of rounding the sum of two 3-digit numbers, the nearest 10, right? What could it be? How big can it be? How big, no matter what it is, how big can it get? Well, let's see. Every time you round, how much do you lose? You either gain or lose at most what? 5. Right? You went 145 becomes 150. You went 40, 44, your low cutoff for which is 5. At most 5. Right? For each. So together, what's the biggest error you can get? Right? So this is the error is no bigger than absolute error. No bigger than 10. Right?
But then if those are 4-digit numbers, you could round to.
Right, but really stick with this. I'm looking at the sum of two 3-digit numbers. Now I look at relative error. What would the relative error be? Would be the at most 10, right? Absolute error divided by the true value. What's the true value? Well, of course you don't know. You don't know, right? But you know something. You're adding two 3-digit numbers. How small can it get? I know, but what is it?
It's less than 10%.
At least 200. Am I right or wrong?
200.
Because each number is at least 100. The two of them you add is at least 200. So this thing, right, the bottom, at least 200. Now, the smaller the denominator of a fraction, the bigger the value of the fraction. Therefore, this is less than or equal to 10 over 200. Correct? Now, this is the thing you might want to learn to make estimate like this. This is what it's all about, making estimates. You may repeat. You want me to repeat this? Down here, true value is what? The sum of two 3-digit numbers. If it's a 3-digit number, how small can it get? 100. So this sum, in no circumstance, would be smaller than 200. Right? So what happened is that n, if this n is bigger than n, then this is true. Now that's one thing. As I said, I'm forced to use fractions. Otherwise, there's no way out of it. But if you have any doubts, keep this in mind when you come to discussing fraction next week. You understand it better. Right? 10 over 3 is less than 10 over 2. That's what it says.
Why is there an equal sign?
Oh,
Because it could be.
you forgot that? What's wrong with it?
But you just said that n was bigger than n. No, not.
No, it's no.
Oh,
Bigger,
okay,
I'm
that's
sorry,
the
bigger
problem
than
then. I
equal.
thought you just said if n was.
But even if I said that, it's still okay.
I don't know why. Should I think? I'll think about it.
I know. You think about that. Therefore, this is going to hold, right? What is it? Just 5%.
5%.
Under any circumstance, an error of 5% is very good. This is why you can give a blanket endorsement to students and say, you want to add two three-digit numbers? You want to check correctness? Round off the nearest 10 and add. You're going to come to something that would give you great assurance as to the accuracy of your addition. Sorry?
I just want to be clear, maybe I missed it. M and N are representing the.
No. Any two integers M and N. Two whole numbers M and N. I'm trying to illustrate why I can say this. Because 200 is going to be at least, this is going to be bigger than or equal to 200. Oh, right? Therefore, the denominator is bigger than equal to the denominator. Therefore, the fractions have this probability. So it doesn't matter what two three-digit numbers are. You always get something no worse than 5%. Now that is something you can sign off by, right? That's worth it. Round off and then get something. Then you can check. You can check accuracy. You can definitely check accuracy. But the blanket endorsement in the book about rounding off to 100 and you can get a good check on the accuracy. That's just, it's not acceptable. But this characterizes all textbook writing, unfortunately. So I want you to get a sense that one, estimation is serious business. In science, that's everything. Experimental scientists, if they don't have an estimate of the relative error, they're out of business in no time flat. So it's serious. If it's serious, that should be taught seriously. If they're not being taught as just a monkey business. So I hope you go back and address this issue with the teacher. As I said, of course, when you do this in grade 4, then if I have a fraction, have a percent, you cannot quite do it. But knowing this to be true, then what it can help you is you are much more careful in making recommendations. You can try to, through concrete examples, to illustrate to your students why what you recommend is good enough. Right? Okay.